This paper is a great start for anyone trying to grasp LLMs because it talks about multiple aspects, from domain-specific fine-tuning to RAG and then multilinguality. So what is it about? ClimateGPT is a domain-specific model family. The models are 5, 2 trained from scratch and 3 fine-tuned on Llama 2, 7 billion, 13 billion and 70 billion parameters models. All models were trained on human-generated instruction fine-tuning data after pre-training. The authors used retrieval-augmented generation to reduce hallucination in the model deployment. Multilinguality was introduced using cascaded machine translation. So what about the results? Despite being 10 times smaller, ClimateGPT 7 billion performs on par with Llama 2 Chat 70 billion on climate-specific benchmarks. This supports the idea that we can use smaller LLMs for domain-specific tasks that will perform on par with much larger generic-purpose LLMs. However, it seems that for domain-specific models, going to larger LLMs doesn't always justify the computational cost. We can see that again when we go from ClimateGPT 7 billion to 13 billion is not much. We can't say much about ClimateGPT 70 billion because the team couldn't do hyperparameter tuning before training the model. So how did they do it? Language modeling is done using decoder-only transformer. The training criteria for this step is simple: predict the next token. No special formatting or template is provided. This step is called by authors continued pre-training. Llama 2 models were used because they scored the highest on the climate-specific benchmark prepared by the team. The models trained from scratch followed Llama 2's 7 billion parameters and even used its tokenizer. For training, the team used NVIDIA's Megatron LM fork by EPFL LLM team. The team observed that higher learning rates might produce better results on the task-specific testing data, but degraded performance on other downstream tasks. It is safer to pick something in the middle not to lose performance and to avoid overfitting. We don't like nerds who can't socialize, do we? What if we can get both in the same person? That would be perfect and awesome. Instruction fine-tuning. Training the model on instruction completion data. This important step will inject the instruction following capabilities into the model. Sometimes it is called supervised fine-tuning, SFT, but in this paper, the authors choose to use IFT, instruction fine-tuning, to distinguish between domain adaptation using continued pre-training and instruction fine-tuning. The team used the high-quality data manually crafted with climate experts. The team focused only on single-turn examples. Although models can chat, but the focus in the data was on single-turn question-answer demonstration. The target was to collect plenty of high-quality climate-specific IFT data, but such data is extremely difficult to prepare and it requires domain expertise on a mass level. The team worked with a small team of climate experts and a larger team of non-experts but with limited domain knowledge. This figure shows the different types of IFT data that the team has used. The first is the manually crafted senior experts interviews. Senior experts are senior professors or researchers in the climate domain. This is the hardest one to acquire, so the team was able to prepare a few demonstrations out of the interviews held. Then the human experts data. The human experts are basically grad students and early career researchers. The team used primary sources of information like research papers and IPCC reports. The human experts were provided with a source document and some suggested questions to help speed up the process. Selecting the seed document to generate IFT data helped a lot diversify the IFT content data around multiple subjects. The automatically generated data out of the primary sources were not found to have an impact, so it was discarded later. Then the non-expert human data, which used the different seed documents that are easier to digest and understand for non-experts, like government websites or reports summaries. To improve on the instruction following, the team has used the public non-scientific out-of-domain data, like Dolly data. The team has also added some safety data generated using a safe model, Llama 2 Chat 70 billion, answering prompts from Do Not Answer dataset, which contains 1,000 of 1,000 questions that models should not answer or should refuse to answer for safety reasons. And then RAG, or Retrieval Augmented Generation. RAG is implemented with high-quality climate resources to increase factuality as well as to extend the system with new knowledge. The team crawled text manually from curated sources and processed them into chunks and embedded these chunks using an encoder to extract the embedding. At inference, the user query embeddings is extracted using the same encoder, and using nearest neighbor search, a related chunk will be fetched and attached to the user query for the LLM response generation. The IFT data included reference paragraphs to train the model to understand adding references. Models usually suffer from mistakes in retrieval, and the models might inject whatever information is out there into the answer. To mitigate this, the authors include a distractor irrelevant document, so the model can learn to ignore irrelevant information even if it comes to the prompt. To select an embedding model, the team used part of the IFT synthetically generated data. Each record of this data consists of a paragraph from a climate-related text and synthetically generated question and answer. The evaluation process tests if the paragraph embedding will be the top one or at least among the top 5 closest embeddings to the question embedding. The answer embedding is usually very close to the paragraph because the answer's information are mostly derived from the paragraph, but that's not the case in the question usually. So the question is most likely close, but not that close as the answer. So the focus was on the question embedding to be very close to the paragraph embedding. Cascade machine translation or multilinguality. To have LLMs that support multiple languages, there are basically two options. The first one is to add multilingual data into the pre-training data and into the IFT data to make the LLM itself supports and understands multiple languages or other languages other than English. The other one is to use English-only LLM, English-only pre-training data and IFT data, and do machine translation. Of course, the second option is a lot easier if we have really good machine translation models. Machine translation is added to support multilinguality. A machine translation from a foreign language into English is added before LLM processing, and then from English back to that foreign language after the response is generated. So first, the user prompt in X language, and then a machine translation translates this X prompt into an English prompt, and then the LLM generates the English response, and then the English response is translated to the X language. The authors published their models in Hugging Face, where anyone can use freely, open source. However, the data were not published. The testing data that the team was working on and created published in the Hugging Face account. The links will be in the description. So this paper is a great stuff for anyone trying to grasp LLMs because it talks about multiple aspects from domain-specific fine-tuning to RAG and then multilinguality. The remaining question for me is how small can we get while maintaining the level of the 7 billion parameters, since it is similar to the 13 billion parameters and 70 billion parameters for domain-specific tasks. So that's it. If you want the written summary of this paper, please check the description below, and please do not forget to subscribe for more videos like this. Hit the like button and see you soon. Bye.